Look closely at ordinary furniture polish, and you'll find a compound containing a hydroxyl group, ethanol. Now look at a bottle of high-end perfume, and you're relying on ethers to carry that fragrance. These chemical classes are active in almost every part of our daily lives. To name the simplest alcohols, the IUPAC system uses a very straightforward modification. Take the name of the parent alkane, in this case, a single carbon methane. We simply drop the E from the end and add the suffix -ol. Methane becomes methanol. Ethers use a different pattern based on their oxygen bridge. Look at this symmetrical structure flanked by two methyl groups. We take one side along with the oxygen and call it an alkoxy group. Here, that's methoxy. We treat the remaining side as the parent chain, methane. Put them together and you get methoxymethane. These consistent naming patterns allow us to describe simple structures with precision, providing a foundation we can now apply to more complex asymmetrical molecules. But what happens when the ether isn't symmetrical? Take this molecule. The oxygen atom acts as a dividing point between a one-carbon chain on the left and a two-carbon chain on the right. To solve this, we use a hierarchy rule based on chain length. The smaller carbon chain, the chota Bhai, stays bonded to the oxygen. This forms our alkoxy substituent. With only one carbon, this side is the methoxy group. The longer carbon chain, the baad Bhai, receives the priority. It serves as the parent alkane. Since it has two carbons, this side is ethane. When we combine the segments, the smaller substituent goes first, followed by the parent chain. This gives us the final IUPAC name, methoxyethane. Naming ethers is a matter of chain length seniority. The oxygen always defaults to the shorter side, leaving the longer side to anchor the name. Let's apply priority rules to branched alcohols. Here is a 4-carbon chain with a hydroxyl group. Our challenge is deciding which end of the molecule to start numbering from. In the IUPAC system, the carbon attached to the OH group receives VIP treatment. It must receive the lowest possible number on the chain. If we start numbering from right to left, the OH group lands on carbon number 3. However, if we number from left to right, the OH group sits on carbon number 2. This follows the lowest locant rule, giving us the correct name, butan-2-ol. Functional groups act as the primary landmarks in organic chemistry. They dictate how you map out and number the entire molecule. There are a few structures where IUPAC accepts traditional common names. When you have a hydroxyl group attached directly to a benzene ring, the compound is specifically recognized as phenol. If we swap that OH for a methoxy group, the systematic name becomes methoxybenzene. However, it is widely accepted to use its common alias, anisole. Let's test your recall. Take 5 seconds to identify the names for these two structures. One is an aromatic ether, and the other is a branched alcohol.
We complete the molecule by filling the remaining carbon valencies with hydrogen atoms. By following the name step by step, the structural formula builds itself. Here is your summary. For alcohols, drop the E, add ol, and give the OH group the lowest number. For ethers, apply the hierarchy rule. The shorter chain bonds with the oxygen. Grab a screenshot to keep these rules handy. While complex structures may look daunting, the IUPAC system ensures that every name provides a clear set of directions for building the molecule from scratch.